Hi, Brian.
Hi,
How
Bob.
you doing?
Pretty good, thanks. How about you?
I cannot complain. Let me introduce us. I'm Robert Wright. This is the Wright Show on meaningoflife.tv, and you are Brian Greene, very well-known physicist and author of books such as The Elegant Universe, The Fabric of the Cosmos, Icarus at the Edge of Time, and The Hidden Reality. I think that's actually the order of their publication.
That is correct, yes.
And you also put on the World Science Festival every year. You've been doing it for 10 years.
Yes.
And you're a professor of physics at Columbia on top of all that, which suggests that you are qualified to do all of that.
Well, you never
You
know.
never know. This is my judgment. You do not have to embrace it. Well, thank you for taking the time. I want to talk about the weirdness of physics, among other things. Not just the famous weirdness of quantum physics, but the weirdness of other aspects of physics, including superstring theory, which you've written about, and and I think you're something of a proponent of. Um, uh, Before we do that, I want to ask you a question about yourself. You are unusual in being both a serious scientist and a very accomplished expositor of science. In fact, I think The Elegant Universe was a finalist for the Pulitzer Prize.
Yes, that's right.
And, I went to this part of the World Science Festival for the first time this past year and saw you on stage doing this kind of multimedia, multi-person art science thing. And I was struck by what a natural performer you are. And I subsequently found out that actually your father did vaudeville for a while. Is that right?
Yeah, that's right. My dad was a comedian and a harmonica player and a singer. And so he dropped out of high school in 10th grade and went on the road as a performer.
So, do you think that has something to do with your urge to kind of not just stay in the office and the lab, but get out there? I mean, both as a kind of literal performer at the festival, but also as just a writer of popularly accessible work.
Yeah, I would say so. I would say, though, that it's a direct attempt to sort of follow in my dad's footsteps, per se. But what my dad certainly made clear to me at an early age was the power of communicating with people in a way that could have real content, but which touches people at an emotional level. That you can really have much more of an impact if someone's feeling what you're talking about as opposed to just, getting a headache trying to follow what you're talking about. So I think that's sort of been with me for a long time. And in a way, I feel like I've got the best collaborator possible in the type of material that I try to talk about, because I don't have to rely on some great comedy writer. I don't have to rely upon some creative person who can come up with mysteries. I've got kind of the universe, right? And so there's this treasure trove of material that one can bring out. And if you can bring it out in a way that really touches people, in a way that they feel moved, I think you can have big impact.
Mm-hmm. Okay. Um, when you said you had the best collaborator, I thought you were going to mention your wife, Tracy Day, who does the World Science Festival. It was an opportunity to be a
She
good husband,
too.
Brian.
She too. You're
You
absolutely
had the
right.
chance. You blew it.
And you with great generosity have given me a second chance at that. And it's true. Tracy Day and I started the World Science Festival together about 10 years ago. 12 years ago, actually, because we needed a couple years to get the first one going. And, many couples who have tried to work together haven't found that it worked out too well. But for us, it's actually a perfect partnership. We just really come together with a single mind so easily on so many aspects, from production to narrative to scientific ideas that we want to bring out to the public, that yes, from that perspective, I have two great collaborators, one of whom is human and happens to be my wife.
Okay. Uh, and she was a TV producer by vocation before doing this again.
That's right. She basically got frustrated with the difficulty of producing smart nonfiction television and was able to shift over all the experience that she had working for ABC News and various other news outlets and bring it to bear on scientific ideas, which has created a novel kind of science experience for the public.
I gotta say, it's a very impressive production, the World Science Festival.
Thank you.
I'm sorry I missed the first 9 years.
Although I invited you one of those years, I recall, and you were busy.
You actually invited me to participate, to be like a moderator or something. I was like going through some sort of career hell that I no longer recall. It was so painful. I had zero time, but I was very flattered. Let's talk about the physics now. Superstring theory has been proposed as something that will lend a completeness, you might say, to physics that it now lacks, or unity. Right now, there are these two big realms, kind of the very small, the quantum physics deals with, very large, I gather, that general relativity deals with. I probably already said something wrong, but anyway, as soon as I say something's not true, correct me. And of course, we would like there to be a grand unified theory. It's an interesting fact, first of all, that so far the assumption that there is more unity there has tended to be borne out by science. I mean, you can imagine a universe that isn't like that, I guess. And that in itself...
Now, you could imagine a universe where the best description you could give of what happens is simply enumerate all the facts that happen out there in reality. And there'd be no patterns, there'd be no shortcut, there'd be no laws that somehow can encapsulate all of those phenomena under one very simple explanatory framework. And that could have been our world. It could have been. And it's an amazing fact that it's not our world, that we look out and baseballs all fly in the same trajectories given the same initial conditions. The moon goes in a very regular orbit, allowing us to predict the next solar eclipse, 1,000, 10,000 years into the future. And this fact is a beautiful unity in its own right by virtue of saying all of these disparate facts come together under a few set of laws. We have been, in some sense, more ambitious and want not only there to be a collection of laws that can describe what happens out there, we kind of want one master equation, one master law from which everything will follow.
Okay. And I guess, and as we said, it has just tended to be the case that, Newtonian physics and so on, you encompass more and more physical stuff in less and less kind of mathematics, in more compressed mathematical form. Now, that's, I guess, you titled the book The Elegant Universe. The universe is elegant in that sense. But there does seem to be something that's happened with modern physics, which is that mathematical simplicity, although in a certain sense it represents conceptual simplicity, in a certain sense it doesn't, because these theories become things that are very hard to comprehend, right?
Well, Steven Weinberg is fond of saying that there's nothing that requires the universe to make theoretical physicists happy. By which he means we look out at the data and we try to formulate mathematical laws that capture the patterns that we see out there in the world. And nobody ever said that the math had to be simple, that the equations somehow had to be very intuitive. That's a human requirement that it'd be great if it were the case, but there's nothing that mandates that that's the way reality should be constructed. So you're right. When we look at modern physics, the math is pretty advanced. The ideas are difficult to understand. If we had Isaac Newton part of this conversation right now, he would catch on pretty quickly, but he wouldn't know the mathematics that underlies the general theory of relativity or the math of quantum mechanics. He wouldn't understand immediately the ideas of quantum entanglement or quantum tunneling or curved space-time. These would be foreign to even the greatest genius of a couple hundred years ago. So that's just how it is. And it could even go further. It could be that the truth is staring us right in the face, but we don't actually have the brain power to grasp what's right out there. And that's the curious feature of all this, that maybe the human brain just isn't equipped to understand the deep truth.
Well, when you look at what it was designed for, it's shocking that we've gotten as far as we have. I mean, evolution, there was no genetic fitness payoff to having a deep comprehension of physical law.
Well, I go further than that. Those who started to think about quantum mechanics and electrons and black holes while meandering on the savannah there, the folks that got eaten. So there was an evolutionary pressure against distraction, against anything that didn't ultimately aid in survival. So yeah, it is amazing that we've been able to go beyond that and figure stuff out.
So one place this issue arises of kind of mathematical elegance, not corresponding to kind of intuitive simplicity, maybe, is in superstring theory, where, again, the idea is you can, in principle at least, encompass phenomena covered by quantum physics and by general relativity in a single framework, but it does have, like, some odd features, like they say it has, I forget how many dimensions, 10, 11, it calls for like 10, 11 dimensions, something like that. And, you know, I have enough trouble going to 4, as Einstein wants us to, you know. Obviously, it gets back to natural selection. I guess we're designed to comprehend 3 in a kind of, you know, simple sense. And when you say to physicists, you know, wait a second, 10 dimensions? That doesn't make any sense. They go, oh, but don't worry, they're really small. I'm like, no, that's a further complication. The dimensions I think of are effectively infinite, right? So I guess the question is, do you not consider that a downside? I mean, what is conceptual elegance in this sense, you know, readily intelligible, is that an asset that a theory would have, or it's just, unfortunately, we just can't ask for that? Mathematical simplicity is the best we can do.
No, I would say that if you see this phenomenon, let's just be concrete as much as we can in this conversation. If you think about the extra dimensions as a nice case study of when you encounter an idea like that in physics, should that be a red flag that says, whoa, we are going down the wrong trajectory? Extra dimensions, that's nutty, we need to turn back. Or is it something that is worthy of attention and perhaps even has deep explanatory power? And that question is ultimately answered by decades of research. And that research has shown us an amazing fact. There are a collection of questions about the natural world that we have no idea currently how to answer. Questions like, why does the electron weigh what it does? Why does it have its particular mass? Or why do the particles that make up matter fall into certain categories? We call them families. There's the electron, there's a heavy version of the electron called the muon, there's a heavier version of it called the tau. So there are all these detailed features of the world, but nobody has any explanation at all for why they are the way they are. Along comes string theory with this very strange and baroque idea of extra dimensions of space. But when we study what those extra dimensions imply for reality, we see potential answers to why the electron has the mass that it does, why the quarks have their masses, why the particles fall into those groupings, those families. And it all comes from the twists and turns, the shape of these extra dimensions of space. Now, that doesn't mean that the extra dimensions are actually there. Only experiment can establish that one way or another. But I think it does help shift your evaluation of the idea away from craziness, extra dimensions, that just means physics has gone haywire, to the notion of, wow, this one idea of extra dimensions may answer a whole collection of impenetrable questions in one fell swoop. And that's where the elegance comes from, that potential power.
And I think, correct me if I'm wrong, I think there's a sense in which there's a kind of conceptual elegance that even a layperson like me can grasp, which is, so I gather the idea is, like, where we think there are different kinds of particles, what there really are is a little circular string, right? Super, super tiny. And all the strings that are where these things we think of as different particles are actually themselves the same. And the difference lies in the vibrations that they are emitting, kind of, the frequencies of resonance, and we kind of, in a sense, have been mistaking differences in frequency of resonance, of vibration, for different kinds of particles. Is that so? And that's a kind of elegance that even I get, because okay, we thought there were different kinds of fundamental physical things. No, they're all alike. They're just doing different things.
Yes, and as you say, there's something quite beautiful about that. And now, using your description, we can go one step further and just say, look, when something vibrates in the ordinary world around us, like a string on a guitar or violin, it produces different musical notes. And we know that a violin sounds different from a piano, sounds different from a cello because of the shape of the instrument. Similarly, the shape of the extra dimensions in string theory plays the role of the shape of the instrument. It guides how the strings can vibrate, and in that way guides the features of the world that those strings give rise to. And that's where you see the role of these twisted up, curled up extra dimensions. They're the body of the physical instrument within which the strings are vibrating. And therefore, the extra dimensions directly imprint the kind of physics in principle that we observe in the world around us. And now, let me just quickly underscore, this is all mathematical at the moment. It's all hypothetical. There is as yet no direct contact between the math of string theory and experimental observational physics. That's the gap. It's not a gap in the elegance or beauty or the craziness of the ideas. It's a gap in actually proving through experimental observation.
So it's a hard theory to test for the time being.
It's a hard theory to test. Moreover, any theory that purports to put gravity and quantum mechanics together will be a very difficult theory to test. So this is not some weird quality of string theory that makes it difficult to test. We're talking about theories that unify, that come together at incredibly high energies or incredibly tiny distances, well beyond the reach of today's technology. So I don't care who you are, if you're putting together gravity and quantum mechanics, the theory that you're going to propose is going to be very difficult to test.
Okay. So let's back up and look at the two kind of theoretical frameworks that superstring theory is meant to unify or encompass. So first there's Einstein's general relativity. And it's funny, in Richard Feynman's book, The Character of Physical Law, he says something like, look, nobody understands quantum physics. There was a time when people used to say that about relativity, but they were wrong. There was always somebody who understood relativity, but nobody understands quantum physics. And in a weird way, I think I have a little easier time with quantum physics because at least I understand where the imponderable sets in. It's like I get it up to that point. Relativity, maybe I just haven't invested the time, but I don't think I have very good conversancy in that. I mean, partly it gets back to conceptualization and our powers of conceptualization. I gather that one thing Einstein did is, we had gravity. The idea was these things exert some force on one another over a distance, which Einstein considered kind of spooky. He'd rather have a different kind of explanation. And his explanation is, well, actually, what is happening is if you think of the space-time continuum, that's where I get into trouble because it's got more than 3 dimensions. It's got 4. But if you think of that, then these heavy objects are kind of warping that such that the things we think of as maybe revolving around them or being influenced by their gravitational fields are kind of rolling along the contours of the space-time continuum created by the warping of the continuum by the heavy things. Is that right?
Yeah, that's right on target. Yeah, exactly.
So that's weird.
You say you don't understand it, but you understand it pretty well.
But that's just, but I mean, I can't conceptualize it. But I mean, I see, yeah.
But you can visualize, right?
Right,
I mean,
visualize.
And it's you're right, it's hard to picture things in 4 dimensions, but the traditional visualization is, a rubber sheet. You take it down to 2 dimensions,
right,
and you put a bowling ball on the rubber sheet. You can picture the bowling ball warping the sheet. You can picture a marble rolling around, sort of like the Earth going around the sun, with the marble being nudged around by the warp in the rubber sheet. And that's a good visualization, not perfect, but a good visualization of what Einstein is telling us. The problem is when you then move over to quantum mechanics, and this is what Feynman was referring to, you don't encounter ideas that are merely difficult to process, and you have to sort of use lower dimensional analogs to capture them. You encounter ideas that just don't seem like they could possibly be relevant to reality, like reality is governed by probabilities, or that there's this thing called a quantum wave function that can link particles over vast distances, such that if you tickle a particle in Los Angeles, it can somehow have an influence instantaneously on a particle in New York.
Which Einstein thought was so weird it couldn't be the case, right? He thought that was a reason that quantum physics couldn't be true. He saw that as an implication of it and said that... Didn't he actually think that would violate principles of relativity because the influence would be traveling faster than the speed of light?
That's right. And in fact, you used the word spooky before in the context of relativity, but Einstein literally used the word spooky in the context of quantum physics for these kinds of processes that, as you say, he thought were clearly an emergent feature of the math, but obviously not a feature of reality. And for that reason, he was like, okay, there's a mismatch between what the math of quantum mechanics says and what reality actually allows to happen. And in the end of the day, he went to his grave thinking that there was a deeper theory that, if we could find it, would do a kind of end run around quantum mechanics, showing that all of these weird features were merely an artifact of the fact that we didn't have the deep understanding as yet. But in the time since, we found that all of the things that bothered Einstein profoundly, all of them have been borne out by observation and experiment. So there may be a deeper theory that may end run all this stuff one day. Who knows? Maybe in the end of the day, Einstein will be correct. I don't know. But the data now is in perfect harmony with the observations and the mathematics of quantum mechanics. It all holds together completely well. There is no issue, especially not the one that Einstein was pointing out.
Right. So whereas quantum physics seems to say that there are some things that are inherently unpredictable, like whether a particle's property of some kind, when you measure it, will turn out to be heads or tails, so to speak, that's just inherently unpredictable. If you ask, well, why was it heads? There's no answer in this universe, literally, right? There's no, that was not determined by anything in this universe, which is pretty weird when you think about it. But Einstein thought, no, there is a hidden variable. There's just something we don't understand. In principle, the universe is predictable. That's the big argument, right?
Well, I would go a little bit different. I wouldn't use the word universe predictable or not predictable. Einstein and the quantum mechanicians all agreed that the math of quantum mechanics did make predictions. They were probabilistic predictions. Right. It would say if you measure that electron, there's a 30% chance you're going to find it here, 20% there, and 50% way over there. And then when you went and did the experiment, Einstein and everybody else agreed that indeed the data showed that 30% of the time you did find the electron over there, 20% over there, and 50% way over there. So all of that was predictions, all of it was borne out, it was probabilistic at its core. But the main problem that I would say that Einstein's objections have evolved into today is the one that you're referring to, which is the quantum measurement problem. Which is, if the math says there's, say, a 50% chance that the electron is in my right hand and a 50% chance that it's in my left hand, when I actually do the observation and I find it, say, in my right hand, how did that happen?
Right.
How do I go from the fuzzy mixture of 50% chance here, 50% chance there, to a single definite reality, which is always what we find when we do an experiment? There's never been an experiment where we find that our measuring device says, oh, the electron's sort of partly over there and it's partly over there. We have never found that. The device always says the electron is absolutely here and absolutely not anywhere else. And yet the math a moment before that may have said that there was a chance the electron could be at a variety of different locations. So how do you go from the fuzzy, nebulous, probabilistic math to the single definite reality of observation? And today we still do not have consensus on how to answer that question.
Well, and in fact, doesn't quantum physics say there will be no answer? If by answer you mean, will we ever have the ability to predict in each particular case, whether it's heads or tails, go further than the knowledge that it's got a 50% chance? Doesn't quantum physics, hasn't it pretty much ruled out the idea that we will ever be able to make predictions in the individual cases that are 100% reliable?
Yes. So there's two issues in there. One is the one that you're describing, and it is quite clear from quantum mechanics that the probabilistic nature of reality is here to stay. So you'll never be able to do some trickery underneath the mathematics and say, oh, you guys doing quantum mechanics, the best you can say is 50% chance here, 50% chance there, but we clever folks, we can get it to 100%. Mm-hmm. We don't believe that that is ever going to happen. But even with that agreement, which is widespread in the community of physicists, there still is a gap. And the gap is still, how do we go from the probabilistic description to the definite reality of observation? And that's a gap that we hope we can fill. Quantum mechanics does not say that that is a gap that won't be filled. Indeed, it is a gaping hole in the equations as they currently stand to go from the probabilistic math to the observations. We don't really know how to bridge that gap, and that's the quantum measurement problem.
Now, do you have a kind of philosophical interpretation of quantum physics? I mean, basically, the philosophical questions arise largely from this kind of merely probabilistic nature of prediction. And, one way it's conceived is, well, before you measure something, when you don't know whether it's going to be heads or tails, you can say that you can think of it as a probability function of if it's more complicated than a binary 50-50, where the particle has a 30% chance of being here, 50% here, 30% here, like a probability distribution, and then at the point of measurement, that has collapsed onto a single point. That's one way to think about it, at least in a mathematical sense. Now, the question is whether you should try to make sense out of that in terms of, what's actually going on. And so you get things at one extreme, you get many worlds, right? The many worlds interpretation, where they say, well, actually, all those probabilities were realized in the next moment. It's just that, unfortunately, the universe had to split into multiple parts to accommodate them. That's right. Of course, completely mind-blowing. And then there are these various other things. There's a Copenhagen interpretation, which I'm not sure I think that's kind of, to some extent, maybe an agreement to not think about it too much, but maybe I'm wrong. There are other things you can say. What do you have a dog in this fight?
Well, you've done a good survey of the possibilities. The Copenhagen approach is largely summarized by physicists as the so-called shut up and calculate approach, which is don't worry about how you get from the math to reality. Just follow the quantum algorithm. Just follow what the math says. And then when you finish your calculation, here's the algorithm for interpreting what it means about reality. And for me personally, I'm very reluctant to accept that picture, because I don't think physics is about creating a sort of black box that can spit out answers. I don't care about oracles that can provide answers that tell me what I'm going to see in experiments. What I'm interested in is pulling back the curtain, opening up the black box, looking inside and understanding the mechanics of reality. And the shut up and calculate approach says don't bother doing that. The many worlds approach is opening up the box and finding one particular interpretation of what the math is trying to tell us. And as you say, it's weird to imagine that there are many copies of you, many copies of me. Anytime there's a probability in quantum mechanics, each probabilistic outcome happens. It happens to happen in its own separate universe. Many people figure that's just too extravagant an interpretation. Miraculously, though, from a math standpoint, it's important to stress the many worlds interpretation is the simplest, most straightforward.
Some people say it's not even an interpretation. It's just what the theory says.
It's what the theory says. And in fact, Hugh Everett III, who was developing this back in the 1950s, his whole motivation was to not burden the math of quantum mechanics with any extraneous baggage. He said, let me just take the bare naked equations of quantum mechanics and see what they're really telling me if I don't bring any prejudice into the game. And that's clearly what the math is telling you. But is it actually how reality functions? That's still an open question. I can't say that at this moment that I have a favorite among the possibilities. The many worlds would be the preferred one, I would say, if it worked. And I think there are mathematical problems with the many worlds interpretation. That's not something that everyone agrees with. There are other folks you could talk to who would say it's a done deal. Many worlds is the correct interpretation. We've dotted the I's, we've crossed the T's, and it's finished. I'm not convinced of that, but there are some who are. My own feeling is that there's going to be a radical step that's going to be taken. I don't think we have the answer on the table as yet. I think there's going to be a radical step that's taken. Maybe it's like Penrose's ideas of consciousness and microtubules in the brain that somehow cause the definite reality to emerge from the nebulous quantum description. I'm not convinced of that either, but I do think that there's a new step. There's going to be a breakthrough at some point, and at that point we'll say, aha, now we understand it.
Mm-hmm. Okay. Now, you've kind of, you've grappled with, I mean, I would say Well, you tell me. Do you consider science for you a spiritual endeavor, or an endeavor that informs a spiritual worldview in any sense?
I would, in the sense that ultimately the reason I do physics is to try to find a way of having a deep connection to, a communion, if you will, with the cosmos. And it feels to me, when I'm deeply studying, say, general relativity, it feels to me that I am having a deeper relationship with the universe, if you will, that I'm somehow seeing into the inner workings, and there's a absolute stunning beauty to it, and there's a emotional quality to it, and you could certainly say it's a spiritual connection that emerges from it as well. Of course, what I'm not saying is that in any traditional theological, any traditional religious sense, I don't go in that direction. But if you, as you did, use the word spiritual in the sense of going beyond the mere intellectual mathematics and sort of feeling something rich and deep and wondrous about the universe from the scientific exploration, then my answer to that would be yes, for sure.
Are you surprised that there haven't been more theologians who have grappled seriously with science? In other words, even if it involves a radical reconception of God, tried to preserve the use of that word, at least, in a worldview explicitly encompassing science?
Well, I mean, obviously it's hard, right? I mean, you have to have a certain DNA, I think, to not to understand these ideas. I think many people can understand them, but if you're going to really immerse yourself in the detailed technical side of things, I think it takes a certain kind of dedication and ability that not everyone is going to have. But I mean, I think you've probably spoken to some, there are some very religious and highly achieving physicists, right? I mean, there are Nobel laureates that I've had the pleasure of having in-depth conversations with, whose view about God is radically different from mine, whose view is much more traditional from a religious standpoint. And it's been very interesting for me to grapple with how it is that they can hold those two views together in a way that makes perfect sense to them. And ultimately, I come out the other side grasping that, that's a real possibility, that you can hold both of these views.
I mean, one thing that only occurred to me a few months ago is if you wanted to argue for an interventionist God, there is this weird, I think, well, you tell me if I'm wrong, there is this weird loophole in quantum physics, which is that, as we said, we don't know what's determining whether, on a given case, you'll get heads or tails. Now, if you imagine this is like a giant computer or something, and the computer programmer is somehow determining that, you could have real influence, and yet still the probability, you could have influence in specific cases, yet the probabilities would work out. So it's like if there's a roulette wheel where we know everything has to be like 1 in 36 chance of hitting every single, that has to work out in the long run. But if you're like sticking a magnet underneath selectively to determine when it lands on 1 and when it lands on 7, you can determine who wins and who loses, and the house would never be the wiser, right?
That's right. That's absolutely the case. And the danger, I think, with that approach is if that is where you're going to insert your theological influence, your divine intervention, you're slipping it into what traditionally, of course, as you know, is called God of the gaps, right? You're saying, as of today, here in the 21st century, there is an opening within quantum mechanics that we don't really understand how this measurement problem is resolved, and maybe we can sort of slip God in there. Now, as I'm saying this, perhaps indeed you should correct me. Maybe your version was that I'm more sophisticated. You're saying even when we solve the measurement problem, there's still going to be a probabilistic quality to quantum mechanics. And you're saying maybe underneath it all, God's sort of tapping, different numbers under the roulette wheel and preferentially causing this or that outcome consistent with the overall probabilities as they would accrue over many runs of a given experiment. And I guess that's possible too. But at that point, you're saying, what role does God play? Because even without that notion of God, we would still make the same predictions. We would still have the same understanding. So I'm not sure, if God is reduced to just stochastic noise, I'm not sure that it played the same role that you imagine.
In this scenario, God would be using what seems to be stochastic noise to conceal the actual interventions. And I guess I'd say the difference between this and God of the Gaps is that the trouble with God of the Gaps has been that, like, you assert that God does this thing we can't explain, and then science explains it, and then you're in serious trouble. But with quantum physics, the quantum physicists themselves are saying, don't worry, this is something we insist we will never be able to explain.
Yes. If that's where you're slipping in, which is where my second thought went. But I guess then at that point, normally we physicists resist the idea of an interventionist God, because that would mean that the equations that we write down only work some of the time. And when God decides to intervene, that's when the equations no longer are telling us what happens, because God's making a choice. But in your version of that, our equations would work all the time.
Right.
And the fact that you would on the side be saying, oh, well, God's doing that would have no impact whatsoever on any prediction, any observation relative to what we would have said if the hypothesis of God being there wasn't part of the story.
And yet,
so from that perspective,
it would have a kind of influence that's never detectable. Right, because because it would determine when the particle is this and when the particle is that, and that might have some kind of significant ramification at the macroscopic level.
That's right.
So, okay. I mean, I'm not really ready to start any religion around this idea. I just thought I'd throw it at you. I mean, I do have a thing, though, with kind of, I'm not a huge fan of the new atheists, I admit. And one thing about modern physics is it does seem to me to reinforce at least the argument for intellectual humility. I mean, there's just a lot of weird stuff. What modern physics is, there's definitely something weird about reality. It doesn't have any specific hint that it's weird in the way religious worldviews have said it's weird, but there's definitely something weird.
Yeah, and it's a weirdness that I have to tell you that I'm thankful for, because it could have been the case that Isaac Newton sorted it all out in the late 1600s, that the laws that we teach to high school kids could have been the laws that describe absolutely everything in the universe, and there was nothing more to the story. And how fortunate it is for us who love puzzles and love to try to understand the universe more deeply, that there's a far richer story that has been revealed through quantum mechanics and special relativity and the general theory of relativity and quantum field theory and the Big Bang and inflationary cosmology, and on it goes, black holes to boot. So how fortunate we are that Isaac Newton didn't sort it all out, that there is so much more rich weirdness to reality. Yeah.
It seems to be the case, and that we may never wrap our mind around all of it. Back to Einstein's worldview, there's something I wanted to ask you about. It is said, this phrase block time, is that it?
Yeah.
Where the idea, again, it gets back to the idea that you should think of time as a dimension kind of just like space, right? For some purposes.
Yes.
And I think one implication of that for him was that, or one thing associated with it, was that the future is determined. I mean, he was a determinist. The hidden variable, interpretation implies a kind of determinism, or at least I think went hand in hand with that in his case, right? So the idea is that, look, the past and the future, it's actually just like north and south. North is already out there. South is already out there. The past is already out there. The future's already out there. It's just that by virtue of our nature as human beings, we can look and see the past, see that part, but we can't see the future. That's kind of Einstein's worldview?
Yeah, I think that's right. So the basic idea is that what makes up reality are a collection of events that happen all throughout time. And what we as individuals do is we take that big, huge block. I like to think of it as a loaf. A loaf is just a block of bread, right? That big loaf of bread. And different individuals slice up that loaf into all those moments that happen at the same time. All those events that happen at the same time. I slice it up one way, and each of my slices of bread are all those events that happen at the same moment from my perspective. But you, moving relative to me, will slice up the loaf at a different angle. which means that those events that you claim to happen at the same moment are not ones that I would claim to happen at the same moment, which means that things that you say are in the past, I might say are in the present, or things that you might say are in the future, I might say are in the past. So the beauty of that is, if we now recognize that your perspective and my perspective and everybody else's perspective, real or hypothetical, throughout the cosmos is on equal footing. There's nobody who's special. Everybody's perspective is just as good as every other perspective. Then every moment in time is the past for some observer. So every moment in time in that sense exists already. And if it exists for you, how could I say it's not real? So if there's an event that normally I would consider to be the future, but if it's in your past, in some sense, I should say, well, yeah, that event must already be out there. It's just an event out there, and I haven't experienced it yet, but somebody else has. And therefore, in some sense, all moments in time are on equal footing. Past, present, and future are equally real. They're all just out there filling out this big cosmic loaf of time.
And is that kind of still accepted even in light of quantum physics? I mean, you might think, in other words, well, Einstein's a determinist, but quantum physics is not deterministic, at least in the predictive sense. It's only probabilistically predictive, so we no longer take that part of Einstein's worldview seriously. You might think that, but I gather actually people take the block time universe thing seriously.
Well, the thing to bear in mind is that the equations of quantum mechanics are every bit as deterministic as the equations of classical physics. As you say, the one critical difference is the equations are predicting probabilities of outcomes as opposed to the exact outcome of what we anticipate happening. But in terms of the math makes definite predictions for those probabilities that are completely determined. So in that sense, there doesn't seem to be any wiggle room, again, for any kind of free will or any kind of intervention. The math just determines everything. So yes, there are versions of the block universe that work for quantum mechanics. There are subtleties, of course. If you have the many worlds interpretation of quantum mechanics, then you've got sort of many blocks. You've got many loaves because the timeline in some sense bifurcates, or if you allow me to use loose language, the timeline kind of splits when many possible outcomes all occur in different universes. But at the level of determinism, there's not much of a change, because the equations of quantum mechanics are just as deterministic as those of classical physics. Now, the one hole of this, again, we come back to is the quantum measurement problem. One day, when we solve that quantum measurement problem, maybe right in there we'll say, aha, here's where indeterminism somehow slips into the story. Or here's where free will slips into the story. Or here where God slips into the story, whatever. Since we don't know how to answer that question yet, we can't determine what the impact on our ontology is going to be.
So what would a solution to that look like? In other words, what exact question would we be answering if we solved the measurement problem?
Well, we would add new mathematics, possibly, to the equations of quantum mechanics. And that new math would say, if the quantum probabilities have this particular shape, like you described a probability distribution earlier, with a 30% chance the electron's here, 20% there, 50% there, and so forth. And now we say, if we now measure the electron and we get one single outcome, here's the new equation that takes us from those probabilities to the one definite outcome. And people have written down these equations. We don't know if they're correct, but there are a whole host of proposals that are on the table. And so this is very doable, but we just don't know which is the right mathematics that will take us from the probabilities to the definite outcome. And since that is uncertain, I can't sit here and tell you that determinism is 100% certain, or that free will is completely gone, or there's no role for anything outside of physics as we currently understand it, because there's a gap in our understanding. But when we fill that gap, then we can have this conversation again, and I can be completely definite on what that new piece of quantum mechanics implies for determinism, for free will, for theology.
Okay. So, one more question about, is the phrase block universe or block time or what?
Yes.
Both, or?
Yeah, because basically it's as if often the metaphor in the past has been the river of time, right? Time flows like a river, sort of a nice metaphor. But in the Einsteinian picture, it's better to think of it as a big block of ice. It's as if this big frozen thing where every moment is just locked in its place. Yeah. All we as conscious beings do is slice it up in different ways.
Which is in some ways oddly consoling. It's like it would take a lot of pressure off if the future were already determined and there was nothing you could do about it. Could lead
right.
you...
But it must be. It must be. Just go back to natural selection. It must be that there is a great deal of survival advantage to having the illusion of free will, sure, to having the illusion that the future is open, to having the illusion of control, because you can imagine your motivation might somehow be different if you didn't buy into those notions.
Right. So in this universe, here's a question. If it sounds too strange, ignore it. It occurred to me while I was listening to this idea, I guess it was Immanuel Kant who said space and time are like a priori categories. We're just kind of set up to assimilate reality in terms of them or something. And here's a question. So if really time and space are remarkably similar in their actual nature, can you imagine an organism, presumably not created by natural selection as we know it, but can you imagine in the universe of physics an organism that kind of flips things relative to us? So in other words, it looks to the future and looks to the past and it sees them both and says, yeah, of course, they're set. But when it looks to north and looks to south, it sees south and says, yeah, I know what south is. South has happened. But north, that stuff just keeps coming at you. We can't see it yet. Can you, sure, is such a creature imaginable in principle?
Yeah, I would think so. I think what conscious intelligence does, it tries to make sense of the world. And you can imagine that sense is so intimately tied to your perceptions that if there's another creature whose perceptions are vastly different from ours, they sort of take in reality in an orthogonal way relative to how we take it in, that their intuition and their explanatory framework would be orthogonal again to ours. There's this, not to get into silly land, but there's this
please.
character
I actually encourage that.
Well, there's a character Q on Star Trek, The Next Generations. I don't know if you follow any of this.
Not a Trekkie, but go ahead.
But anyway, that's a character for whom time is quite different, for whom the expanse of time is just there. And Q finds humans amusing or irritating at times, but amusing that we take in time in this very linear, very sequential manner. So, yes, I can imagine that there could be intelligence out there that would take in reality differently from us.
Okay. Now, just a couple of random questions. There was an astrophysicist at Rochester named Adam Frank who he does a blog for NPR. And he wrote a piece for this really actually very interesting website magazine called Aeon, A-E-O-N. In which, as I recall, he said, let's face it, I hope I'm not putting words in his mouth, the worldview emanating from modern physics cannot really be described as materialistic. I mean, he wasn't getting all wooish on us, but he was saying, and in a way, your own writing about superstring theory, you emphasize that it's not like these circular strings at the root of everything are made of anything. They don't have like the strings, I guess, don't have diameters even. Maybe they're infinitely small. They aren't made of any. So I think he was actually framing the argument more in terms of quantum physics. But there's actually a lot of parts of physics you could point to and go, so wait, there's no actual stuff at the bottom. I mean, and do you have a view on that, or do you think it's kind of a semantic question, or what?
Well, it certainly is a semantic question ultimately, because I do think there's stuff at the bottom, but the stuff at the bottom may be so radically different from the stuff at the top or at the midway point, wherever we are in the grand scheme of things, that it's hard for us to ascribe it the same kind of reality that we ascribe to, a cup or a table, right? Again, it would have been interesting, or less interesting, but it would have been curious if Newton's view of basically a lot of little billiard balls bouncing around and coming together to make tables and chairs and stuff, if that was all that there is, and it's not. So there are fields, electromagnetic fields, nuclear fields. Those don't really have the same kind of tangible quality as a table does. But we're all, I think, at this stage of the game, pretty comfortable with electromagnetic fields, right? We feel static electricity, we rub the balloon in our hair, it sticks to the wall. It all is a little abstract, but we can grasp it, right? Whereas, you go to somebody in the 1500s and talk about electromagnetic fields, and it'd be like, what? It would be as weird as some of the concepts that we're talking about today with extra dimensions and vibrating strings. The one place that I will say that some people go and I don't is they say, look, at rock bottom, it's not stuff, it's not material, it's not field, it's information. Rock bottom of reality is just information. And I can't buy that because, yes, information is critical to our understanding of reality, but information needs to be embodied. It needs to be instantiated in stuff. Mm-hmm. And that stuff needs to have some reality beyond the abstract notion of information on its own. Right. So, yes, information married to some kind of instantiation probably is a reasonable way, as of today, to think about what the rock bottom stuff of reality is.
So, in fact, if you sign on with the people who say maybe we're in a computer simulation, so at the bottom it's all code. Now, it's true on the one hand that we could probably never verify that because that's presumably not, perceptible to us. On the other hand, it would actually restore a materialistic framework because, as you say, code is always embodied, instantiated in physical stuff. So that's actually a materialistic worldview.
It is, because ultimately there is a computer that's running that code. I mean, if you just have the code abstractly as information versus having that code brought to life by virtue of running it in a device, that's the difference that I'm talking about between information and information instantiated. And yeah, it could be, and I'm open to the possibility that we're living in a simulation. It sounds nuts, but there are reasons for taking that idea moderately seriously. And it could be that there's some kid in a futuristic garage who just came home from school yesterday, flipped on the universe making program, and here we are talking about it.
Okay, now here's an interesting thing to me about that, to get back to God a little bit. If you say, I'm a deist, I believe God created the universe and then let it go, doesn't intervene, I think the average scientist looks at you like askance. Certainly many would.
But accept that as a logical possibility.
Yeah, it is a logical. My point is, more people I think more scientists look at you askance if you say, or maybe more just kind of people who think of themselves as having a scientific point of view. More people look at you askance if you say that than if you say, I think we're living in a simulation. And yet, they're the exact same thing, right? I mean...
Yeah, that's right. And in fact, to tell you the truth, when I first began to think hard about the idea that we might be in a simulation, it, for me, was a bit of a transition where for the first time, I sort of felt like, yes, this universe could have a creator. This universe could have a creator, and it doesn't require anything supernatural. It doesn't require going beyond any naturalistic description of how reality functions. It just amounts to having a sufficiently clever and a verisimilitude-like resemblance to reality being instantiated in a computer. So that kid who I mentioned a moment ago who came home from school could be the creator of this universe, and there's nothing supernatural about it whatsoever because that kid is governed by the uber set of physical laws that govern everything that's happening out there in the world. So from that perspective, you can have your creator and you can have your naturalistic description of reality at the same time. So you can have your cake and eat it, so to speak. You don't have to give up a description of reality that makes us physicists comfortable, and yet at the same time allow for a creator.
But in that scenario, the algorithm that was unleashed at the Big Bang would be a product of design in some sense.
That's right. It would be intelligent design.
Yeah, although not in the sense that the advocates of intelligent design mean that, because they mean that natural selection can't account for I think that's what they mean. I have trouble figuring out.
Yes, of course. Yeah, so the language becomes a little bit dangerous, and I would not want to be quoted out of context. But yes, this is a version of a scenario where this world was created by an intelligence, but it has very little to do with the traditional notion of intelligent design.
Okay. Now, anything you want to say on consciousness quickly? Seems weird to me, but whatever.
Say it again?
Anything you want to say about consciousness? We've covered everything else.
That's such a small topic. Look, I mean, I think consciousness is one of the big towering mysteries. I like to think about the big mysteries as, how did the universe get started? How did life get started? How did consciousness get started? Where does this phenomenon come from? And if you ask me which of those three questions is going to be the most difficult to crack, I can well imagine it's going to be the consciousness one, which means to me one of two things. Either it's a non-question, and we're just making it into more of a big deal than it actually is. And all the consciousness is the physical sensation of a certain kind of information processing that takes place in our brains, and that's all that there is to it. There's nothing more to it, just accept it. Or it may be that consciousness is something radically different than anything that we've been able to describe using physics. And if you take it to the extreme, there are some very smart people who have introduced an idea that's been around for a very long time of panpsychism. That maybe what's really going on is electrons, photons, quarks, they all have a little amount of proto-consciousness, and only when they come together in the right organized frameworks do you get the kind of macroscopic consciousness that we humans experience. That would be a kind of radical step to move in that direction, and those are two ends of a long spectrum of possibilities. And where we're going to come out, I don't know.
Yeah, but it seems to be not strange to think in one sense or another it's a property of the universe, and maybe something that accompanies certain kinds of configurations of physical stuff, maybe those that are involved in information processing of certain but the thing I like about it is it gives life, I think, meaning. I mean, the fact that it's like something to be alive, the fact that there is subjective experience, I think makes life a very special thing.
Oh yeah, I would go even further. I think, whenever you talk about meaning of life, it has to be, I think, in juxtaposition to death. And what does death mean? Well, in one view, death means the end of the body and the end of consciousness. Right. And another view, where consciousness is not so profoundly tied to the physical form, if it's something else, if electrons have consciousness, then it reveals the possibility. It gives hope for the possibility that consciousness could persist after death.
It assumes more diffuse form, presumably, but in some sense.
In some sense, well, I think there are many perspectives on that. It's beyond testability, at least as far as I can know. So you're just in a game of wishful thinking at some level, which doesn't mean it's wrong. It could be that certain wishes are fulfilled in the way reality is composed. But I think these deep questions of life, death, and meaning are intimately connected to consciousness. Without consciousness, it's very hard to even see how we would engage with these ideas. Right? There's this notion of a philosophical zombie, right? Not the zombie we see in horror films, but the notion that there could be intelligent forms, like human beings per se, who go about their daily business executing the very same behaviors, but without any internal life taking place inside their heads. And in that sense, they would be zombies. And that does not seem to contradict the laws of physics as we understand them. And yet, if you did have a species of beings of that sort, I think issues of life, death, and meaning would have a very different role in their lives.
Right.
So it is this internal chatter that takes place in our head that makes us strive for something beyond the physical.
And as you say, it seems, if you have, scientific worldview, there could be organisms that are very effective, and it's not like anything to be them, because in principle we can explain all the behavior that natural selection would favor just in terms of the physical information process. It doesn't seem like there have to be feelings associated with running away from something that could kill you, and yet there are. So, I mean, even in that kind of relatively reductive view of subjective experience, that it's just an epiphenomenon, it's still weird that it's here.
Yes.
Because it has no apparent function.
Totally. You can certainly imagine, it's very easy to imagine because we can do it today. You program some artificial robot to run away from fire or run away from danger, and it's doing exactly what you say. It's fleeing. It's the flight reaction to danger. But nevertheless, I don't think that there's anything inside that entity which is experiencing fear or experiencing some kind of anxiety or terror. And yet we do experience fear, anxiety, terror, happiness, and wonderment, and all the things that make life worth living. And why is it that we have an internal life? Why is it that we have an internal existence? And again, either it's a trivial question, and it simply is the way it is when there's a certain kind of complex information processing, or it's a deep question, which is revealing something about reality that we have only been tapping into in the most crude way, and ultimately we will hopefully tap into in a much more deep way, and as many people who take this perspective suggest, have a complete new way of thinking about reality.
Well, I would say we've covered about enough ground.
Yeah.
I'm trying to think of a deep question we've left unplumbed. I'm sure there are some, so maybe if you have time down the road, I'll try to talk you into doing this again. But
sure, it was a lot of fun.
It really was a lot of fun. Thank you so much. Anything you want to plug? I mean, are you working on any books? Of course, people should. The I guess 11th Science Festival. It will be the 10th or 11th, the World Science Festival next.
It's coming up the 11th.
It's the 11th next year. Everyone should show up at that. It has more than one locale, right? I mean, it's a New York thing, but it's also in other places thing.
Yeah, it's a New York thing. It's also in Australia, which is our sister festival, which is all good if people happen to be around for those. I am working on a book right now. I won't say much about it, but I would say that the themes that we've touched on here today play a prominent role in that book. So it's a somewhat different direction for me to go, which I think you at least would be interested in. So maybe I'll have one reader.
You have one. I can guarantee you have one reader.
There we go. That motivates me to get on to the next.
I'll tell my friends, and I have 2 friends, so you got 3 right there.
3 readers right there. Although maybe you want to share the book. But yeah, that's the main thing that I'm focusing on right now.
Okay, well that sounds great. Any timetable or?
Yeah, I have to deliver next summer, so sometime probably a year and a half.
Okay.
From now
well, I look forward to it. Thanks again so much, Brian. This was fun.
My pleasure. Thanks.